So hello everyone, welcome to Understanding Virtualization Memory Management Concepts. My name is Kit Colbert and I'm an engineer at VMware, and Fei Guo is here today and he helped me work on this presentation. So, let's see. This talk is really divided into three sections. The first is giving you some background into the memory management concepts that will enable you to sort of understand the statistics and best practices we'll talk about next. And those are the two other sections, and with that's really the bulk of my talk today. So before getting into the concepts, though, let's talk a little bit about motivation. Now, I've been giving this talk for, 3 or 4 years, and the reason I started giving it was because of the fact that I kept hearing again and again the same questions come up around virtualized memory management. People had very common questions and very similar misunderstandings. So I figured, well, you know what, let's try to create a talk that will actually go through and answer those questions. That way, instead of individually answering questions for people, I can just point them at this talk. So with that in mind, before we can answer a lot of these questions that people have been asking me, what we need to do is take a step back and delve into the concepts, and that will give you the mental model to be able to answer not only these current questions that I listed before, but also any other questions that might come to mind. So a couple of things. I want to say that this is a discussion of concepts, and somewhat high-level concepts. We can certainly delve down into details as much as you'd like. However, that's going to take more and more time, and we only have 60 minutes. So because of that, and to aid in just simply grasping these concepts, I'm describing them at a somewhat high level and a somewhat different way than you may see them described other places. But this is actually okay. I think what I'm trying to stay true to the underlying concept, even though some of the implementation details may be slightly different. So in case you see this stuff presented differently elsewhere, that's actually okay. It's just a different view of really the same thing. So how many people here are familiar with the concept of virtual memory? Okay, seems like most people. Just for those that aren't, virtual memory has actually been around for quite a while. I think it's back in the 60s they came up with it. And essentially the idea behind it is that you can create a uniform memory address space that's presented to applications and even to the operating system. It gets rid of all the subtleties and irregularities of how memory is actually mapped out in the hardware with various regions off limits to the BIOS because of the BIOS and because of the VGA memory and other types of things. And it essentially just gives the operating system an extra level of indirection, so it can do all sorts of management of memory without the application knowing. Now, just the way that the operating system does this for applications, the hypervisor actually does it for operating systems, for VMs. So the hypervisor just adds another layer to this. So we have virtual memory, physical memory, and then what we call machine memory. And for a hypervisor, the machine memory is actually the real physical RAM. Now we have these three different layers, and as I said, these things are actually address spaces. So a piece of memory has a certain address in one and may have a different address in another, or may not have any address in another one. It's up to really each layer to manage that. But instead of talking about, so what you can do is a simplification, and again, this is a bit of a simplification I'm doing for this talk. You can say, well, the virtual memory is pretty much managed by the application, while physical memory is managed by an operating system, and then the machine memory is managed by the hypervisor. And indeed, instead of using these terms, virtual, physical, and machine, we can just call them by the layer that uses them, the application, the OS, and the hypervisor. So we have application memory, we have OS memory, and we have hypervisor memory. Again, a bit of a simplification just for this talk. Now, in addition to just the application and the operating system, we also have this VM, which encompasses both. And as we'll see in just a second, the VM actually takes on properties of both the application and the operating system. So let's delve into exactly how each layer manages its memory. Now, for an application, it manages memory actually pretty straightforwardly. It manages it how you would naively think it should, in that the application, when it first starts up, has no memory, and it explicitly allocates that memory from the operating system through a syscall interface. Similarly, when it's done with that memory, it will then go in free by making a similar syscall. So the operating system can actually track all this. And what this means is that there's an explicit memory allocation interface with the operating system. So again, pretty straightforward. Now, how does an operating system manage its memory? Well, it's a little bit different. It's different because when the operating system first boots up, it assumes that it's the only thing on that machine. It assumes that all the memory, the physical RAM on that machine, is its to use as it pleases. Secondly, there is no concept of memory allocation or memory free in the hardware. The hardware doesn't know this. It's all just memory. The hardware has no concept, this one's allocated to this thing, this one's free. It doesn't know that at all. So actually what happens is that the operating system has to create that semantic, create that meaning. And it can do this in a variety of ways. A couple of examples here are free list, but it could use any sort of data structure to do it. And in fact, each operating system does it somewhat differently. So how does a free list work? Okay, we first boot up an operating system. Now, it's got all this memory there, and it needs to go through and sort of figure out what to do with it. So it says this one piece of memory, it's going to make that its allocated list. Selects another piece of memory, it makes that its free list. So now it has an allocated and a free list. Now it goes through all the rest of its memory, and I'll just highlight a few sections here. And it adds all those regions to the free list. Again, because all these regions are currently free. Nothing's using them yet. There's no applications running. The operating system has just started to boot up. Now let's say that, And it's important to note that this free list is a piece of memory. And this memory has data in it. And this data is memory, or are memory addresses. These memory addresses are simply pointers to these other regions of memory. So now an application starts up. What's it going to do? It's going to ask for a piece of memory. So when it does that, the operating system will take a piece of memory, remove it from the free list, and again, that's just, removing its address from the free list and adding it to the allocated list. And then it'll give that piece of memory to the application and create a mapping between the application's virtual memory and the physical memory that the operating system manages. Similarly, the application will probably allocate some more, and maybe it'll free something, and so the operating system will move that thing back to the free list. So there's an interesting thing that happens here. Memory becomes allocated or free depending on which other piece of memory has a pointer to it, depending on which other piece of memory has that memory's address in it. Now, does that make sense to everyone? VM memory allocation. So what we're going to see here is that the VM starts up like an application in that it has no physical memory allocated to it. But unlike an application, this VM is the operating system essentially right now. There's no applications yet. So an operating system doesn't allocate memory. It just starts using memory. Again, because the operating system assumes that it owns all the memory. So what's it going to do? It's just going to start touching memory and say, this thing should have this value and that thing should have that value. Now when that happens, the hypervisor has to sit there and say, hold on a sec. I see that you're trying to write to that piece of memory. So I need to go and allocate a piece of machine memory of real physical RAM here so that you can actually go ahead and do that right and actually make progress and then create a mapping. So the operating system sort of goes and does, So it sort of goes and does that. So that's the allocation side of VMs. Now let's look at how VMs free memory. Well, again, remember that the guest operating system doesn't really ever free memory back to the hardware. Again, the hardware has no concept of allocated or free. Instead, it's the guest OS that creates it. So when the guest frees a piece of memory, it just adds it to its free list. So what this means is that some piece of memory somewhere in the guest operating system has changed value. And by virtue of that change, this other piece of memory is now considered free. What does that mean? Well, it clearly means that the hypervisor isn't aware when the guest frees memory. It doesn't know which region of memory the guest free list is. It doesn't even know what data structure the guest operating system is using to represent what memory is free and what memory is not free. So because of all this, the hypervisor is really not sure when a piece of guest memory is free. So let's take another look at this just to make sure everyone understands it. We're looking at the VM from inside the VM, from the guest OS's point of view. So here, since we're the guest OS, we know what our free list is. We know how much data is on it. We know which regions of memory are free. So the application allocates some memory, allocates some more, maybe frees a piece of memory, allocate some more, freeze it, so on and so forth. So what you see is a pattern where there's sort of a back and forth between allocations and frees. And in the end, when that application will exit, the operating system will free all of its memory. Now let's look at it from the other point of view, from the hypervisor's point of view. Now the hypervisor, again, has no visibility into the VM. It is very much a black box. It's just memory changing values, right? And how do you know this one memory changing value over here is a free list when it could be this one over here? Or maybe it's Oracle updating its database cache. Who knows? So instead what the VM sees is it sees the operating system ask for more memory and more and more and so on and so forth. It never sees the frees because the frees are just memory modifications. They're just writes to memory. So because of this, the hypervisor can't reclaim memory through guest frees. So what do we do about it? There's really two options here. We can do nothing, or we can do something. Now, boiling it down to its basics, but the nothing route, what does that mean, really? It means the hypervisor is unable to reclaim guest memory. So once a guest uses it, until that VM is powered off, the hypervisor can't reuse it for other VMs. So that means when a VM boots up, you have to be sure to reserve all that memory, the full size of the VM's memory, for that VM, and not allow other VMs to use it, just in case the VM will eventually use it. Now what does this mean? Obviously it means inefficient use of your RAM, because of the fact that the VM may or may not be using that memory, right? Or we can do something about it. And this means that the hypervisor has to innovate various techniques to be able to reclaim this memory. And that means, furthermore, that the VM memory does not need to be pre-allocated. It can be allocated on the fly as the VM tries to use it. And obviously this means that you can have more efficient use of your memory because of the fact that a VM's only using what it's really using. It's only consuming what it's really using. So what are these techniques? I think you're familiar with pretty much all of them. The first is transparent page sharing. And the basic idea behind this is, why do you have to have multiple copies of something when you only need one? If you have 4 Windows VMs, exact same version, exact same patch level, why do you need 4 copies of the executable code in your physical RAM? Why not just have one? So that's exactly what transparent page sharing tries to do. It'll walk through all the physical RAM, looking for identical pieces of memory, and then sharing them. And again, because of this virtual memory layer, this indirection that the hypervisor has, it's able to do this without the guest OS knowing anything about it. And moreover, it's able to do it securely in such a fashion that if the VM tries to write to that piece of memory that's shared with other VMs, we'll make a copy, the hypervisor will make a copy, and that VM will get a private copy. The other VMs aren't affected. So again, pretty straightforward. I think most people are familiar with this. Now, ballooning. So I'm assuming most everyone here has heard of ballooning and knows the basics behind it. What I want to do today is give you a bit different view than you've probably seen of ballooning, a bit more of the fundamental underpinnings of it to give you a better understanding. So before diving into the mechanics of it, let's take a step back and figure out what exactly ballooning is trying to do, what exactly the situation is that we're trying to remedy. Well, here's the situation. We have a hypervisor that needs to reclaim memory. It's got a bunch of VMs running. Some VMs are more important than others. So the hypervisor needs to take away memory from the unimportant ones and give it to the important ones. Now, while all this is happening, the guest operating system running inside of that VM doesn't know any of this, right? It's just running inside its VM. It's happy. It doesn't even know it's on or in a VM. It thinks it's on a physical host. So what we want to do here is we want to try and alert the guest operating system to the fact that it needs to free up some of its memory. And so what we do is we actually artificially create memory pressure inside of the guest, inside of the VM. So we try to take that memory pressure that's there at the hypervisor layer and sort of push it up inside the VM. Thus, the VM will take action, the guest OS in particular will take action to remedy that. And we do this through a driver inside the VM called the balloon driver. So that's the background. Now I want to walk through an example of inflating the balloon. And as you know, there's two steps to this. There's inflating, that's taking up memory, and then there's deflating, and that's allowing the guest to use more of that memory. I'm not going to go over the deflating step, but this is the first half of it. So, inflating the balloon. Let's take a look at the situation now. We have a hypervisor, and we see that it has 8 pieces of memory that are currently allocated. Now, we look inside the VM, pardon me, and we see that 3 pieces of memory are currently allocated. And we currently have 6 pieces of memory on the free list. And we want to reclaim some memory from the guest. So, the first thing that happens, the balloon driver allocates memory. So bam, there it goes. It calls in, the guest free list shrinks a bit. Now, the balloon driver does something that's called pinning that memory. Now, what it means to pin memory, it's a standard operating system term. Windows, Linux, pretty much all the operating systems support it. And what this means is that the application asks the operating system not to page or swap that memory under any circumstances. It says, this is important memory to me, either for security or for performance. Don't swap it. And so the operating system can oblige and say, yes, okay, I won't swap it. So that's what the balloon driver asks. The balloon driver says, please do not swap this memory under any circumstances. Now, the guest may choose to reclaim some memory, and that will depend on what its free list, whether it's very small, as we have the case here, just 3 left, or if it's very big, maybe it won't reclaim memory. But let's skip over that step, and I'll drill into it some more in a second. Now, while all this is happening, the balloon driver goes out of band to tell the hypervisor what memory it allocated. So the hypervisor can follow all the arrows, since the hypervisor knows all about this stuff. It can follow the arrows and figure out which pieces of machine memory the balloon driver actually allocated from the guest. The hypervisor can then free that memory. And now the hypervisor has more free memory. So if we take a look at what happened here, we see that while before we had 8 pieces of memory allocated by the hypervisor at the hypervisor layer, we now have 5. And where before we had only 3 pieces of memory allocated at the VM layer, we now have 6. So we took that difference of 3 and pushed it from the hypervisor layer up into the VM. So how could we do that? Why did that just work, right? Why does not, the world not blow up? So again, we had these 3 pieces of memory, and the hypervisor just taking them away and doing something else with them. So let me ask you a question, and feel free to shout out a response if it comes to you. Why can't, during the normal course of operation, why can't the hypervisor just take memory away from the VM? Just take it away. What would happen? I can hear a few things. Just shout it out. Anybody? Guest would fall over. Okay. Why would the guest fall over? So it's referencing memory it no longer has. But it would have it because when it tries to access that piece of memory again, the hypervisor would create a fresh copy. Now that fresh copy would have all zeros in it. But it would still fall over. And the reason is because the guest OS assumes a particular value will be in that memory. It assumes that what it writes to memory doesn't change. That's why we have ECC memory, is to make sure this sort of stuff doesn't happen. That's why the hypervisor can't just go and do that any old time. But why can we do it now? Well, the real question is, what in the VM assumes that that particular piece of memory has a value, has a specific certain value that it's depending on? Well, there's only so many choices. We sort of have the application level, and we have the guest OS level. Now, at the application level, I didn't draw this here, but there's also besides the balloon driver, there's also other applications. Now, obviously, other applications, due to memory protection, can't see the balloon driver's memory, so those guys are out. What about the balloon driver? Well, it actually doesn't care. Why? Because we wrote it, and we told it not to care. So, it's an easy one. That's why we have it in there, in fact. We have it in there exactly for the reason that it won't care. That the memory that it allocated can suddenly turn all 0, and it's fine with it. It's not using it. Okay, so the balloon driver, not an issue. No problem there. What about the OS? Well, the OS doesn't either. Why is that? Well, it's because the memory is allocated to the balloon driver, so the operating system's like, well, I'm not going to touch it, because if I touch it, I'll be bad for the application. But moreover, it's also because that memory has been pinned. So the operating system can't give the memory to anyone else, any other applications. So it's out. So this means that nothing in the VM relies on the memory's value for correctness. That's why the hypervisor can safely reclaim memory this way through ballooning. That's why the hypervisor can just yank that memory out. Because it knows, it's guaranteed, that nothing in the VM relies on a particular value for that memory. The operating system could go crazy, start accessing that memory. Hypervisor would allocate a fresh piece of memory, all zeros, no problem. So that's why ballooning sort of works. Now, the other thing I wanted to touch upon was that a lot of people have this connection between ballooning and guest OS swapping. And I want to say that they're not necessarily a direct connection. Guest OS swapping is definitely a possible side effect, but not a necessary side effect. And let's see why. We basically have two possibilities here. We have the guest free list, and it has tons of free memory. Balloon driver allocates some of it, and the guest OS is like, no problem, I got plenty of free memory. Everyone's good, no need to reclaim anything. So, no swapping necessary inside the guest. But if you're in a different situation, the guest is already pushed back toward the wall a bit, it's pretty low, the balloon driver takes even more of that, now it's like, wait a sec, I'm critically low, let me reclaim some memory. So we leave it up to the guest operating system to choose whether it needs to swap or not. The hypervisor has no clue about this. It just allocates the memory it needs. The guest OS does what it will, and that may include swapping. Okay, so that's ballooning. Now again, swapping, I think you're all familiar with as well. And I think it's important to delineate the fact that this is hypervisor swapping that I'm talking about and not guest OS swapping. Swapping can actually happen both at the OS layer and at the hypervisor layer. This is strictly at the hypervisor layer. And all we're doing here is just transferring a piece of memory from physical RAM to disk. And the OS doesn't know anything about it. As you can see, the OS layer hasn't changed at all. It's just the hypervisor's layer that changes. Now, swapping is great because it's a big hammer and can be used forcefully against VMs that aren't cooperating. You saw how long balloon took, how many steps it took. And it may not happen fast enough for the hypervisor. So the hypervisor can use swapping as a last resort. However, it's not great because the performance of it is not nearly as good as ballooning or transparent page sharing. However, we've introduced a new type of reclamation called compression in vSphere 4.1. And compression tries to make swapping a little bit less painful. So the idea here is that instead of writing this data out to disk, and we all know how slow disk accesses can be, especially compared to memory, why not try to compress it first? If the compression goes well, then we'll keep it in memory, but compress by at least 50%. And if it doesn't compress well, we'll swap it out as normal. So again, the decompression side of this will be extraordinarily fast because it's just a memory access, running the decompression algorithm, and you're good to go. The only other point I want to make is that compression only runs when memory needs to be swapped. It's not like transparent page sharing where it runs all the time. The hypervisor doesn't just randomly go off and try to compress pages. Instead, what it does is if some region of memory needs to be swapped out, the hypervisor first tries to compress it. Oh, and we have a little graphic here. Okay, so you see how now multiple pieces of memory fit into one region there. Okay, and there we go. Now, when do we reclaim memory? When do we invoke ballooning, compression, or swapping? Transparent page sharing is always running. As I mentioned, ballooning, compression, swapping all take a little bit more effort. So when do we enable them? Well, there's this concept of memory overcommitment that I believe everyone's familiar with. And memory overcommitment is when the total amount of guest memory, guest configured memory, is greater than the amount of host memory. Now, when that situation occurs, it means that it's possible for the VMs to exhaust all the host memory and yet still want more, because not all VM memory will have an arrow to hypervisor memory. Pardon me. So, when do we reclaim memory? Well, if you're not overcommitting memory, then memory will never be reclaimed through ballooning, compression, swapping, because there's really no need to. No other VM will need it. Every VM can be fully satisfied. If your memory is overcommitted, then the hypervisor actually monitors the amount of free memory in the system, and as it drops toward the threshold, ballooning will start. As we said, ballooning takes a little bit of time, so we kick it off a little bit early. Now, if ballooning is not able to get things done, then we kick in swapping as a last resort as the free memory passes the threshold. So, that's a little bit about the background, the concepts. Are there any questions? One way at the back. Why do you only compress data if it compresses by at least 50%? That's a good question. So I think we had done a bunch of studies to look at the efficacy, how well compression worked. And I'm not too familiar with the specific details of it, but somehow 50% came out as the number that helps the hypervisor reduce the amount of used memory in the system, while also allowing for good, decent performance. So I think there's sort of a balance there, and somehow they came out with 50%. I don't actually know the details of it, though. But that's a good question. One more. Anybody? I'll be available afterwards, so you can feel free to ask me then. Okay. Now, let's delve into statistics. So before getting too far into it, I want to say that the most important thing to understanding memory statistics in Virtual Center is that some statistics measure the physical memory, while other statistics measure machine memory. Again, we have these two different layers here, and we have two sets of statistics that measure each. So there's a couple of examples here. Now, how does this play out? Well, let's take a couple of examples. First, we have memory shared and memory shared common. So memory shared is a bit of a mind bender of a definition, but I'll walk you through it. It's the amount of physical memory, so again, the amount of memory at the VM layer, whose mapped machine memory, you follow the arrow down to the hypervisor layer, has multiple pieces of physical memory mapped to it. So does that piece of memory at the hypervisor layer have multiple arrows going to it? If so, then the piece of memory you're looking at in physical memory is shared. So we see that if we do that, there are, 6. Now, memory shared common. Memory shared common is the amount of machine memory at the hypervisor layer with multiple pieces of physical memory mapped to it. So the hypervisor layer with multiple arrows to it. Again, we see there's 3. The difference here, obviously page sharing. The accounting at the physical layer sort of, in some ways, double counts, but not really in other ways, because it's what the guest sees. So there's sort of a discrepancy between what the guest sees and what the hypervisor sees. Now, another example, memory granted versus memory consumed. Memory granted is the amount of physical memory mapped to machine memory. So it's the amount of memory at the VM layer with an arrow down to the hypervisor layer. So there we can easily see 9 pieces. Memory consumed, the amount of machine memory that has physical memory mapped to it. So again, we're looking at the machine memory layer and looking for arrows coming down to it. And there we see 6. So the key difference here is page sharing. There are going to be other reasons as well. Sometimes swapping or ballooning can cause a few of these issues, a few of these mismatches. But in general, the key is that these two things are actually measuring different things. So when we take a look at VM statistics like active, granted, or shared, these all measure physical memory. And it's sort of hard to compare that to host memory, which is measuring a machine memory value, right? The size of the memory on the host, the physical RAM. So in the end, you have to be very careful when comparing these two different types of metrics, that they actually measure different things, and thus they can be very different. For instance, look at memory.active. You say this VM is actively using so much memory, and you add up all your VM's memory active, and maybe it's possible that memory active number is bigger than the amount of host memory you actually have. Why? Because of page sharing. Because all that Windows executable code that's being run frequently has been shared. So again, you can get these sort of confusing things if you're not very careful to look out for which ones are physical and which ones are machine. I don't want to spend too much on this diagram. This is more of a reference. I think this talk should already be posted on the web. If not, it'll be posted very soon, so you'll be able to see this. I won't go through it, but this gives you a visual idea of what some of the statistics are in vSphere. Okay, so now what are the important metrics to look at? First, we have a VM. Memory.consumed, obviously a pretty important one. It just tells you how much machine memory has currently been allocated to that VM. Secondly, we have size target. Size target comes from ESX top. How many people here use ESX top, out of curiosity? Oh, great. Good, at least 50%, maybe 60%. That's awesome. For those of you that don't use ESX top, this is a great stat. Unfortunately, we don't have it in vSphere as of vSphere 4.1. I personally just added this stat to vSphere a couple of days ago, so next release, it'll be there. This is a great stat. So size target tells you how much machine memory the VM is entitled to. And its entitlement is based off a number of things, off its reservation, off its limit, off of shares, off of its memory size, off of its active memory working set, all sorts of things. But this is a very accurate description of how much memory the VM actually deserves based on its relative priority with other VMs. Now, memory.active, again, this is an estimate of how much guest physical memory, not machine memory, but how much guest physical memory the VM is actively using. What this means is that you can't actually compare directly mem.active with size target. Ideally, you could. It would be a great comparison to make. But right now, mem.active measures physical memory while size target measures machine memory. So mem.swap-in rate. This is a good one for looking at, for monitoring actually, to look at how your VM's doing in terms of memory. Swap-in rate simply tells you how much memory is being swapped in by the hypervisor. I'll talk more about it in just a second. The other one to monitor is CPU.swap-wait. This one's similar to swap-in rate, except for the fact that swap-in rate measures megabytes, while this one measures time. So this tells you how much time the VM is spending waiting for a swap to come in from the hypervisor's swap file, or from the VM swap file. Obviously, the larger the number here, the higher the impact that VM's performance. So, two good things to monitor, swap wait and swap in rate. Now, if they're consistently greater than 0, or if you have trending software and they're higher than they normally are, ideally they should be at 0 most of the time. But if either of those two things happen, then that means there's a potential problem with that VM. It could be suffering. Now, you want to find out why. Well, mem.active is a useful one. That'll tell you what the VM's workload is. If it's higher than normal, then more than likely there's some sort of workload spike happening. Otherwise, you can look at size target. And if size target is lower than normal, what does that mean? It means, well, this VM is suddenly not as important as other VMs, and the amount of memory that it gets has been lowered. So there's a couple of things you can do for both of these situations. You can increase the reservation for the VM. That way, size target is bounded by, at the low end, by the reservation. Or you can just move that VM or other VMs off the host to free up some more memory. But again, swap-in rate and swap wait are two very useful ones for monitoring whether your VM is being affected by memory issues. The other tidbit I like to talk about is in vSphere 4.1, we have these two new counters, virtualdisk.read and virtualdisk.write. Now, by themselves, they just measure how much I/O is going to each virtual disk of the VM. But a clever thing you can do is actually put the guest OS's swap file on a separate virtual disk. That way, any activity that happens to that swap file will show up as I/O under virtual disk.read and write. Thus, you can actually use these counters to monitor how much in-guest swapping is happening. And again, the idea here is you have to actually put your, configure your guest to have its swap file or swap partition on a separate vdisk, and then these counters will just sort of work for you. Okay, now onto the host. Like with a VM, we have mem.consumed. This is the total amount of memory that's been allocated both for VMs and for system services. So this tells you how much you have in total, and then you can subtract that from your total amount of memory for the host to figure out how much headroom you have. However, a slightly better way of doing it is to use this derived stat. And again, unfortunately, this stat doesn't exist by itself in vSphere. So that's why I'm saying you have to do a computation. Today, we have mem.active. Mem.active for a host is simply the summation of all the running VMs on that host's mem.active. But again, remember what I was saying. Mem.active measures physical memory. So there could be some double counting when you're looking at the host. There could be some of that memory that's shared. So we have to figure out how to get rid of that sharing amount to see how much machine memory is actually being used. So what do? Well, we can actually multiply by the ratio of shared common to shared. Remember, shared common is the amount of shared memory at machine level, while shared is the amount of shared memory at physical level. So that ratio can be applied to active memory to get a statistical estimate of what your machine active memory usage is. And the machine active memory usage is, I think, probably one of the most important metrics that we can have for a host. It's very unfortunate that we don't expose it. This is another one that I just added a couple of weeks back. So this will be in the next release. You don't have to do this computation anymore. Now, reserve capacity. The other thing you want to be very mindful of, in addition to how much memory is being used, is how much reservation is being used. So you do want to reserve enough memory for the VMs to have their active working sets in physical RAM, but you don't want to over-reserve memory, and you don't want to completely overcommit your hosts on reservations. If the host has no extra room, that can actually cause performance problems for the VM. The VM has something called overhead memory that the hypervisor uses to do various types of things, keep various metadata about it while it's running, but also to do some performance enhancements. And that size of that memory can change as the VM's working set changes. So it's important to look at reserve capacity and make sure you're keeping a little bit of breathing room for the VM's overhead memory to grow if it needs to. And again, for monitoring, swap-in rate is a great one. That will tell you the aggregate amount of swapping that's going on across all your VMs. And again, the same way as for a VM, you can look at it, and if it's higher than normal, then you possibly want to move some VMs off that host or investigate if there's some workload spike going on with one of the VMs. Now, there's a couple of other stats. I don't want to go over them in too much detail. I think this is more of like a useful reference. So I'm not going to talk to it, but if you see something you have a question on, find me afterwards and we can discuss it. For ballooning, for swapping, and also in a second for compression. So then we have compression. Now again, compression is new in 4.1, so all these stats are also new in 4.1. Okay, so now we can take all the knowledge, all the statistics that we've learned and apply it. So let's start out with the VM. Now, we know that transparent page sharing is always running. That's great. A lot of customers say, well, should I really enable ballooning for all my VMs? Or can I rely on hypervisor swapping? Or what should I do? You know, there's these rumors that ballooning can affect performance. Is that true? Not that I've heard of. But there's a lot of FUD about it. So in answering this question, I want to highlight this memory hierarchy I've created. And again, this is a simplification for this talk. But in the end, we have three leaves here that are interesting. Active memory, which is allocated memory that has been recently used or accessed. Idle memory, that's memory that's allocated but has not been recently used. And then free memory, and that's memory that's not assigned to any application or to a VM, for that matter, from the hypervisor's point of view. So now we're going to look at the OS layer in terms of these three regions. Now, how does ballooning work? Well, as you know, ballooning relies on the guest OS to do swapping if necessary. So if the guest OS believes swapping to be necessary, it'll do the smart thing, and it'll move out memory that is, it'll allocate memory that's free. It won't even swap. So that's great. I'm getting ahead of myself. So it'll select free memory first, and if all the free memory is used up, it'll start swapping idle memory. But the key is that it doesn't touch active memory. Okay. Now, how does ESX swapping work? Well, again, ESX, the hypervisor, doesn't know what's going on inside the guest. It doesn't really know which memory is free versus idle, because, again, it doesn't have access to the guest's free list. So essentially what happens is ESX swapping just sort of picks a piece of memory at random and takes it. So that means that ESX can actually swap the guest's active memory. Now, what does that mean for performance? Well, obviously it's not so good. So we have a swing bench VM here, and on the x-axis we have the amount of memory that's been reclaimed either through ballooning for the blue line or for swapping for the pink line. On the y-axis we have throughput that's normalized for the zero memory reclamation case. Now you can clearly see that with ballooning we stay pretty close to that same performance of no memory reclamation. But with swapping, it goes downhill pretty quickly. And why is that? Again, because swapping is randomly choosing memory, and it happens to a lot of times choose memory that the VM's actively using. That means the VM has to wait for that swap out, and then wait for it to get swapped back in, wait for your disk to do all its I/O, and that's going to hurt performance. So ballooning generally outperforms swapping, almost always. That means that you really do want to install VMware tools and enable ballooning for all your VMs, regardless of the workload. But in addition to doing that, there's also a couple of snafus you can hit. One of the most common ones is not providing enough swap space inside the guest. If the guest needs to swap, it needs swap space to swap to. Linux had this terrible thing where if there wasn't enough swap space and it needed to reclaim memory, it'd just go around and start shooting processes randomly. It'd even kill a NIT sometimes accidentally and bring the whole OS down. So these are the sorts of issues you need to watch out for. Just make sure that the swap space is large enough inside the guest, and be sure that whenever you change the VM's memory size to also make the swap space inside that guest larger to accommodate the extra memory. And as I said before, another tip that you can do is place the guest swap or swap file or partition on a separate virtual disk, so you can use these new counters in vSphere 4.1 to monitor the in-guest swapping from Virtual Center. Now, let's continue out this tape. We see that we've reclaimed a bunch of memory from the VM already, but the hypervisor needs more. So the balloon driver allocates more. Now what happens? Well, the operating system obliges, and it starts reclaiming some memory. But look what happens. It runs out of free memory and idle memory, and so now all it has left is active memory. So if you ask it to reclaim too much, ballooning will eventually start taking active memory and thus impacting the VM's performance. So now we take our graph from before, and you notice very conspicuously the right side of the image is not there. So if we draw it out, look what happens. You can see that as we continue to increase on the x-axis and get higher and higher levels of memory reclamation, eventually we start eating into the active memory working set of that swing bench database, Oracle database test. And you can see its performance go downhill. So again, what this means is that you really need to make sure that for best performance, you're keeping your VM's active memory in physical RAM, in machine memory. So how can you do this? Well, there's a couple of steps. First, get the right VM memory size. Why? Because of the fact that if your VM memory size is too small and the working set inside the VM is so large, the guest OS may be forced to swap and there's nothing that the hypervisor can do about it. You've run out of physical memory address space. So you need to make sure that the VM's memory size is greater than even a spike in your mem.active. Secondly, so that takes care of the physical memory side of it. Now, of course, we need to take care of the machine memory side of it. That's what you set the VM memory reservation for. And again, that should be set slightly above or around the VM memory, the active memory size. And this just makes sure that the active memory working set won't be swapped out or ballooned out accidentally. You can use the performance tab to monitor this stuff, or we have a great product called Capacity IQ, which will also do all this stuff for you and actually suggest VM sizes and everything. Now, getting onto the host. How many VMs can I put on a host? This is a very consistent question I get. How do I know when my host is at capacity? So on and so forth. And this is obviously just in terms of memory. There's other issues as well. But in terms of memory, simple answer is as many as will fit. And, people get frustrated when I say that. But it's not a very satisfying or even useful answer, right? So let's try harder. As many whose active memory will fit in physical RAM while leaving a little bit of breathing room for any sort of workload spikes. Now, going back to memory overcommitment, I want to define and tease apart two different types of memory overcommitment. And this is something that I've literally just sort of come up with myself. I don't think you'll see it anywhere else. But I think it's a useful concept. So the first is what I call configured memory overcommitment. And this is generally the sense of memory overcommitment that's usually there when people talk about it. What this simply means is that you add up all the VM's configured memory sizes and then divide by the total amount of memory available for the VMs on the host. Then there's active memory overcommitment. And that's taking all the VM's active machine memory and dividing by the amount of memory available for VMs on the host. And again, you'll see some equations here on how to derive both of those. Now, what's the impact of each of these? Well, here's the thing. For configured memory overcommitment, I would argue there is 0 to negligible VM performance degradation. While with active memory overcommitment, if you hit that situation, there's a very, very, very high likelihood of potentially serious VM performance degradation. So why is this? Well, configured memory overcommitment. So you see here that in physical RAM, we have some free memory, some idle memory, and some active memory. Parts of it are not in physical RAM, but the key is that all of the active memory is in physical RAM. And remember, from just a few slides ago, you saw the graph of Swing Bench. As long as its physical memory was still in RAM, you can balloon away all that extra stuff. Doesn't matter. Barely affects its performance. But if you do commit so much that you're overloading active memory, what that means is that there will be parts of active memory that are no longer in physical RAM. So what happens there? Well, those parts that aren't in physical RAM are still getting used, so the VM's going to try and access them, which means the hypervisor has to fault it in, which means that now the hypervisor has to swap some other piece of active memory out, but then the VM needs to access that, so it's got to swap that back in, so then something else needs to go out, yada, yada, yada. And you can see how things can grind to a halt fairly quickly. So the takeaways here are that configured memory overcommitment are great, and this is something that VMware has been preaching for years, that this is something you want to do because you're maximizing the value of your physical RAM by keeping the active memory in it. So you're actively using that RAM for something. Now, if you push it too far, you're going to end up in the active memory overcommitment phase. And this is why I've separated them out, because active memory overcommitment is definitely not recommended, and it's not good. So you want to monitor things using the stats that I've told you, and you can use those equations I've given you to figure out how much headroom you have. You can use the machine active memory estimation, so on and so forth. And in the end, you can maximize the amount of active memory in physical RAM while not hitting active memory overcommitment and losing performance because of it. Now, what's the deal with compression? Why do we introduce it? Well, it's exactly to let you push things just that much closer in terms of your total configured overcommitment and push it that much closer to active memory overcommitment. Now, you can see from the graph here where memzip should be compression, but I didn't know how to change it. It wouldn't let me. So anyway, memzip is compression. So you can see as on the x-axis, the host memory size gets smaller while the total amount of VM memory stays constant. There's less overall memory to be used for the VMs. At first, it's not too much of a problem, but eventually you can see that we start hitting the limit of the amount of active memory of the VMs. And with swapping, the blue line, you can see things go downhill pretty quickly. With compression, though, you can see a markedly less downward slope. So compression does give you a little bit of breathing room there, where swapping would make you pay a high performance penalty. So again, what compression lets you do is just get that much epsilon delta closer to active memory of 1, but not quite getting there, and thus not quite hitting your performance degradation. So in the end, the question can be restated. How do you ensure that you don't hit active memory overcommitment equaling 1? And the simple explanation is just to use memory reservations. Again, if you know what your VM's active memory is, if you've trended it, things like Capacity IQ can do this for you, then this can all be set up and things will just work. And that way you don't even need to think about it. DRS, HA all work off of memory reservations. They all abide by them. Thus, if you're setting it properly, such that it's encompassing all the active memory of that VM, then you're done with it. It's good to go. Okay, so we're basically out of time. We have about 10 minutes for some questions. Very quickly, concept summary. The guest doesn't free memory in a typical sense. Because of this, the hypervisor is not aware of when guests freeze. So the hypervisor has some techniques it can use, but it only uses those techniques when memory is overcommitted. With statistics, you'll see the useful ones here. Again, be sure to keep in mind that there's a difference between physical memory statistics and machine memory statistics. Finally, all the best practices we talked about. Enable ballooning, provide sufficient swap space, so on and so forth. Keep that active memory overcommitment metric in mind. Make sure you're not going too close to it. And, okay, that's new. So I just want to say to everyone, it's a real pleasure speaking. I think we send out surveys by email now rather than you filling them out here. It's great not only for VMworld but also for me to get feedback on this. So if you wouldn't mind going and filling those out, I'd really appreciate it. And with that, I think it's time for Q&A. So any questions? Yeah. Good question. So the question is performance degradation on swap. How is it affected if your swap file is on a solid-state disk? Excellent question. So we actually, that's one of the things we're looking into is using solid-state disks as a sort of second layer of caching for swap. So yeah, solid-state disks are awesome. I mean, their read times are so insanely fast that you're not going to see nearly the sort of nosedive that you see today with the spinning disks. I don't know, do you have any data on SSD and how it compares to normal spinning disks in terms of performance? We have it. Come talk to us afterwards, and we might be able to give you some more details. But all I know is that we are looking at how can we utilize these solid-state disks, if they're in a box, just to use them as a cache, to give another layer of indirection, another layer of performance. Yeah, so that's a good question. Yeah? Yes. So a question about the slide deck. I have a lot of animations, and it's true. It doesn't look quite as pretty in PDF format. If it was in PowerPoint format, you could walk through it, but unfortunately it flattens everything out, so it can be a little bit confusing. The positive side, this was all recorded, I believe, on this Camtasia stuff, which makes a video of all of this. So you can go back through and watch the presentation. You'll see all the builds again. But yeah, it's a good point. I like to have the builds in there because I think they're illustrative, but they don't do so well. They're illustrative in the moment, but they don't do so well sort of post-mortem. Yeah. Yeah. Good question. So do reservations, at least for things like Windows, offset the usefulness of things like resource pools and other types of memory management because of the fact that Windows touches all of its memory when it first boots up? That's a great question. So luckily for us, Windows, what it does is it touches its memory, but it actually zeroes all of that memory. So what you see in Windows is actually a huge spike at first because it's just touching all sorts of stuff. So you see its active working set go crazy, right? But transparent page sharing will kick in and actually find all those 0 pages and pretty much make them all as one. So if you have some 16 gigabyte VM, it's going to maybe use a gigabyte of that actively. It's going to touch the other 15 gigs, make them all zeros. But eventually that transparent page sharing will find all those and it'll come back down. So it is true, actually, to go one step past your question, that even if your VM has a reservation, transparent page sharing is still in effect on it. So for instance, if you have a reservation of 100 megabytes and your VM uses 50 megabytes but then zeros another 50 megabytes, those 0 pages will be reclaimed through transparent page sharing, even though your VM has a reservation. So the reservation really only applies to unique data. And there's been some debate back and forth as to whether that's the right thing to do, but that's the way it behaves now. So I would say that it doesn't invalidate any of the memory management techniques we have for things like resource pools. Yeah?
Okay, can you touch a little bit more on the deflation of the balloon? Like, basically, from what I understand, your Windows guest is seeing that now as pin memory, and it's no longer inside the free list. So does that mean that, does your balloon driver zero it out after it gets it?
Right, okay. Good question. So the question is about the deflation side of ballooning and how exactly that works. So a couple of things. When the balloon driver is done using its memory, it will actually unpin the memory and then free it back to the operating system, just like any other application would. So remember that the balloon driver is actually getting its instructions from the hypervisor. The hypervisor is telling it through this sort of back channel and saying, hey, I need you to go reclaim 50 megabytes. And then later it says, okay, you can free up 25 of that. So literally all the balloon driver needs to do is just unpin the memory and then free it. Now, the operating system has to deal with all sorts of applications doing all sorts of stuff. So the operating system will normally zero the memory before it should zero the memory before it hands it out to someone else. But the idea is that when the operating system gets it back, once it touches it to zero it, say, then the hypervisor will allocate a fresh page for that guy. So that's when you see the balloon driver freeing its memory, there should be a subsequent rise, at least initially, before transparent page sharing kicks in for those 0 pages. But does that answer your question? Okay. There's one in the back.
When you're talking about loading up your host with VMs, you said be sure to leave some memory for peak. Do you have a rule of thumb for what would be a good number? 8%, 4 gig? Is there anything?
That's a great question. So the question is, okay, my consumed memory can be 100%, that's fine. But we're talking about loading up VMs with reservations, and that really goes back to active memory. So how full should I make my host in terms of active memory, in particular machine active memory, the equation I showed you? That's going a bit further than my thinking's gotten, I think. Unfortunately, I don't have good empirical data on this. A lot of this is literally just me thinking about the problem and saying, okay, what do I think is the best way to solve it? So I haven't done all the sort of formal, full due diligence to figure out what the right numbers are. I would agree with you. It's probably somewhere around 75 to 80% in terms of how high you want to push it. And again, compression can give you a little bit of breathing room there, and maybe, as this gentleman said, SSDs can give even more breathing room. But I think that's what it is. I think what you can do is you can sort of start off at like 50 or 60%, and then you can take it up a notch every now and then and see how your spikes go. And if the spikes are still well within range, then things should be fine. And so I think that is what I want to see as we go forward. I want to see us, as VMware, introduce better techniques to allow you to get higher and higher percentages of machine active memory on your host. So as a good rule of thumb, I don't unfortunately have a great one, but if I were to guess, I would say 75 to 80 sounds in the ballpark to me. What would be reasonable?
What about SQL Server VMs? Because, whatever you sign up, just as a
Right. So let's see. Are we at limit? Shall I take this outside or? Okay, I'm saying yes. So I'm going to be right out front, and you guys can feel free to come talk to me, and I'll be happy to answer as many questions as you have. So thank you. I'll see you outside in a second.